This is that if xi is equal to xi1 plus I times xi2, so if the solution xi is a complex vector valued solution of xi prime equals a xi, homogeneous linear differential equation with constant coefficients, then xi1 and xi2 are real vector valued solutions of the homogeneous equation star H. And I should specify here too. So if xi equals xi1 plus xi2, it's a complex vector valued solution of star H and xi1 and xi2 are real vector valued functions, then xi1 and xi2 are also real vector valued solutions of star H. The proof of this is relatively straightforward. We know that xi prime is equal to the matrix A of T times xi, and this actually holds for more generally if you have a homogeneous differential equation with depends on T, so even non-constant coefficients. So let's make that explicit here, that A of T could also depend on some T. So if xi prime equals A of T times xi, we know that this means then that xi is this complex vector valued function, where xi1 and xi2 are real vector valued functions. So this will be xi1 prime plus I times xi2 prime, where I is the imaginary unit. And A of T times xi will be the matrix A of T times xi1 plus I times xi2. So this expression can be rewritten as the matrix A of T times xi1 plus I times A of T xi2. And because xi1 is a real vector valued function, xi2 is a real vector valued function, and A of T is a matrix of real coefficients, we have to equate the real and the imaginary parts of these two complex vectors. So we have to conclude that xi1 prime is equal to a of t times xi1, and that xi2 prime is equal to a of t times xi2, or t and I. So let's go through and consider the following example. We'll consider the linear system. Xi prime is equal to the matrix -1/2, 1, -1, -1/2 times xi. This is our matrix A. Step 1 is to set up the characteristic polynomial P of lambda, which will be the determinant of A minus lambda times the identity matrix, which will be -1/2 minus lambda times -1/2 minus lambda minus -1 times 1. Which results in the characteristic polynomial being 1/4, which is -1/2 times -1/2, plus 1/2 times lambda, plus 1/2 times lambda, plus lambda squared, plus 1. Which is the quadratic polynomial lambda squared plus lambda plus 5/4. The eigenvalues are the roots of this polynomial. So when P of lambda equals 0, where this is going to be the quadratic formula, then lambda is equal to -b plus or minus the square root of b squared minus 4 times a, which is 1 times c, divided by 2 times a. So the eigenvalues will be -1/2 plus or minus 1/2 times the square root of 1 minus 5, which is -1/2, plus or minus the square root of 4 times I, because we have the negative value under the square root. And so the eigenvalues are lambda 1, which is -1/2 minus the square root of 4 over 2 times I, or just 2 over 2 times I, which is just I. And lambda 2, which is -1/2 plus I. The eigenvectors are going to be complex, because the eigenvalues are complex numbers, but they're still going to satisfy the eigenvector equation. A times u is lambda 1 times u, and A times v is lambda 2 times v, which can be solved using standard methods from linear algebra. So you can solve a given system like this in many different ways. The easiest way is probably using the reduced row echelon form. But you have to remember that these values are going to, in general, be complex. This is going to give us the equation negative 1/2 1 negative 1 negative 1/2 times u is equal to negative 1/2 minus I times u1, u2 and A is negative 1/2 1 negative 1 negative 1/2 times v is equal to lambda 2, which is negative 1/2 plus I times v. So when we go through and solve this, you get this will be negative 1/2 u1 plus u2 is equal to negative 1/2 minus I times u1 and you also get negative 1 times u1 minus 1/2 u2 is equal to negative 1/2 minus I times u2. And again, I want to emphasize that for larger systems, you can go through and use row reduction to solve for the eigenvectors. But for smaller 2x2 systems, sometimes it's easier to see the solution just by going through and doing one of your standard solution methods. So substitution or elimination, right? These are all procedures that can be used to solve this system. But ultimately what happens is that you get that the eigenvector, when this is solved, is of the form S times the vector I1, and you get that the eigenvector V is of the form S times negative I1. And so the eigenpairs for this system are this eigenvalue with this eigenvector, and this eigenvalue with this eigenvector. So the general solution then xi of t will be of the form c1 e to the lambda 1 times t times u plus c2 e to the lambda 2 times t times v. So xi of t will be equal to c1 e to the negative 1/2 minus I times t times u plus c2 e to the negative 1/2 plus I times t times v, which is negative I 1, and I'll put in u as well. The vector I1. And we have to do a little bit more now because, from this theorem, we can go through and actually get a solution that is in terms of only real numbers by cleverly rewriting this expression. But we have to go through and do that right now, and because this is not in the form, xi here is not in the form of xi1 plus I xi2, where xi1 and xi2 are real. Luckily, this will be possible to go through and do directly. Now, before going through and trying to simplify this, let's kind of take a long, hard look at what exactly we have so far. So here we have two fundamental solutions. The first is phi1 of t is equal to e to the negative 1/2 minus I times t times the vector 0, 1 plus I times 1, 0. And phi2 of t is e to the negative 1/2 plus I times t times the vector 0, 1 minus I times 1, 0. In general, when we have a pair of complex eigenvalues and eigenvectors, this is going to be what we see. So what I'll do is, do the general simplification below. Let's suppose that lambda 1 is some alpha minus beta times I, and lambda 2 is some alpha plus beta times I, and the corresponding eigenvectors u and v are going to be some real valued vector A minus I times b for some b. So A and B are real valued, and v is going to be some A plus I times b for some real valued A and b. And the idea here is the following. So we'll just consider how we can simplify phi1 of t. We can rewrite it as e to the negative alpha t times e to the negative I times t, or times beta t, times A minus B times I, and likewise phi2 of t is going to be equal to e to the alpha t this should be e to the alpha t times e to the I times beta t times a plus b times I. And both of these can be simplified using what's called Euler's identity, or Euler's equation, Euler's formula. This is one of the most fundamental formulas in all of mathematics. I go through and I prove this for my Calculus 3 students. This is that for any real value theta, e to the I theta is cosine of theta plus I times sine of theta. So this is relatively straightforward to prove using Taylor series and a little bit of complex mathematics, complex number theory. But the idea here is that we're just going to take this and use this, apply it in both of these expressions right here. And the ultimate end goal is going to be essentially to go through and take a look here at this theorem that I just proved for you, which is that if psi is psi1 plus I psi2, so we have a complex vector valued solution where psi1 is a solution, psi2 is a solution, then psi1 and psi2 are also real vector valued solutions of the homogeneous form of the differential equations. And the idea here is that we're going to show that the real valued part of this phi1 and phi2, as well as the imaginary part, are both linearly independent solutions of our differential equation. So in order to do that, we need to find the real valued part and the imaginary valued part of phi1 and phi2 and kind of compare these two things. So this is why we're using Euler's formula here. So phi1 of t is e to the alpha t, and cosine of negative beta t, which is just going to be cosine of beta t, and then plus I sine of negative beta t, which will be negative I sine of beta t. So this is the this part right here, and then we have to multiply this by a minus b I. And doing a quick FOIL here, we're going to get cosine of beta t times a, the vector a times cosine of beta t, times negative I sine of beta t times bi, negative. The negatives cancel out. You get I squared, which is negative. This is minus b sine of beta t. And this is the real valued part. And then you also have to do the other cross multiplications because we're doing a FOIL here. So you have cosine of beta t times b times I, negative. So cosine of beta t times b cosine of beta t. And then you also get negative I sine of beta t times a. This is a times sine of beta t. And this entire thing is in parentheses. This is all being multiplied by that e to the alpha t from before. And so this is pretty cool. This basically gives us two separate, actually linearly independent solutions. The first one is e to the alpha t times a cosine of beta t minus b sine of beta t. Okay, this first solution we'll call psi1 of t. and we have minus I times e to the alpha t b cosine of beta t plus a sine of beta t, which we will call xi2 of t. This entire thing right here is xi2 of t. So lastly, phi1 of t is equal to xi1 of t plus I times xi2 of t. Sorry, minus I times xi2 of t. And what's pretty cool is you can actually go through and do this exact same thing for phi2 to show that phi2 of t will actually end up being xi1 of t plus I times xi2 of t. So these two things are just complex conjugates of one another, which makes a lot of sense. So they're each of these individual solutions have to be linearly independent from one another, but we also have, based on what we've got here for xi1 and xi2, if you take a look at the Wronskian between these two, or coming from these two solutions, these are actually linearly independent from one another as well, and they're both real valued solutions, which is very neat. And this is essentially it now. So we have xi1, we have xi2. From the previous theorem, we have that these two things are both solutions to the homogeneous form of the ODE, and we now essentially know how to deal with any scenario for the solution to a linear constant coefficient system when we have complex eigenvalues. Now, it's important for me to point out that the above solution procedure only really works if the matrix A consists of only real valued entries, because of the fact that this is the only time that we're guaranteed to have eigenvalues and eigenvectors come in complex conjugate pairs. So that's an important point to remember, that this above kind of simplification is only for our real valued matrices A. So the big takeaway here right now is that the general solution to this problem, corresponding to these two eigenvalue-eigenvector pairs, the complex conjugate eigenvector pairs, is going to be some constant C1, which is the constant of integration, times xi1 of t plus some constant C2 times xi2 of t. Which in long expression is going to be this times C1 plus C2 times psi2, which is this right here. And so what I want to do is go through and just kind of finish the problem that we were working on before to show you the exact full solution to that problem. I'm going to move a little bit back to the example, and you'll recall that in this example we had that the eigenvalues were complex conjugate pairs. Alpha 1 was negative 1/2 minus I, and lambda 2 was negative 1/2 plus I. This means that our alpha value is negative 1/2, and our beta value is just positive 1. And we also have that the values of the eigenvectors are of the form U was equal to 0, 1 minus negative 1, 0, I. So this is our A vector, and this is our B. And the eigenvector B corresponding to lambda 2 was vector 0, 1 plus negative 0, I. Right, this is again A, and this is B. So I just copied the formula that we just found here, and I'm going to plug in the exact values for this problem, and then just simplify to get the exact solution for this example problem. So our alpha value is negative 1/2. Our A was 0, 1. Our B was negative 1, 0. And then same thing here, alpha is negative 1/2. B is negative 1, 0. And A is 0, 1. And oops, the beta value is just very simple. It's 1, so I'm going to just remove beta from each one of these other expressions that I wrote down, just for simplification's sake. And there you have it. So this is the correct general solution to the homogeneous problem given in the example. Now we can kind of clean this up a little bit, make it a little bit nicer, and this is true that you can always do this in general if you want to. So it'll be a little bit longer if the eigenvalues and eigenvectors are more complicated. But the idea here is that the first thing is to notice that this can be simplified greatly by doing out the vector mathematics here to get that. This is the same thing as, it'll be C1 times this, 0 times cosine, negative 1 times sine times negative 1. It'll be C1 e to the negative 1/2 t times sine of t plus C2 times e to the negative 1/2 t cosine of t, then a negative sign. And for the y component, it'll be C1 e to the negative 1/2 times t times cosine of t. And then lastly, plus C2 times e to the negative 1/2 t sine of t. And lo and behold, this can actually be simplified even more by using a little bit of matrix algebra, matrix multiplication. You notice that this is the same thing as, well, we can factor the exponential out of this entire expression, e to the negative 1/2 times t times the matrix sine of t cosine of t negative cosine of t times, or not times, just cosine of t sine of t and all of this. So this matrix right here multiplied by the constant vector c1, c2. So remember what this is. This is the general solution to this problem, psi of t. And this right here is the fundamental solution matrix, phi of t, for this problem. So all in all, this is very neat. This also allows us to immediately set up an equation for both c1 and c2 in terms of the initial condition for the problem. Specifically, this equation is psi of t, or xi of t is equal to psi of t, the fundamental solution matrix, times c. So what that means then is that the initial condition xi at some time t naught is some vector xi naught, we get the equation psi of t naught, whatever this is at t naught, times c, matrix multiplication, has to be equal to xi naught, which means that c will be exactly equal to the inverse of the matrix psi of t naught times the initial condition vector. Which means that the full solution to the general homogeneous problem is going to be psi of t is equal to psi of t times psi of t naught inverse times xi naught, just like we mentioned in the previous lecture. So this is a very neat result and very, very powerful.